Hello BC Calculus students, this is Mr. Johnson and this is the third video for section 8.4 and we're going to tackle our last convergence test, which is the ratio test. So congratulations for getting this far and for getting to your last convergence test. This is certainly one of the most common ones. I'd say that over the 10 tests you're probably looking at the geometric series test, the p-series test, and the ratio test as probably the most common ones. Many of the other ones are also utilized on a regular basis, but the ratio test is going to be one that we will end up using even more so as we look into the next half of chapter 8. So it's a very important test. The test is in three parts, basically. So the first part is that you take the limit as you look at a sub n plus 1. So in other words, you look at the next term divided by the previous term. So you take a sub n plus 1 divided by a sub n, take the absolute value of it, and if you get a value L that is less than 1, then the series is absolutely convergent, which means that it therefore is convergent. Number two, if you get a value that is greater than 1, or you get a value that's infinite, then the series is divergent. Number three, if it is equal to 1, then you cannot determine what is happening based on the ratio test. So no conclusion can be drawn. So those are the three parts. So obviously we're looking at typically taking the first one. We're typically using the ratio test to determine convergence itself. All right, let's go on to the next page and look at the first example. Okay, so our first example, I'm going to show you essentially what happens when the ratio is equal to 1. So the first one we're going to do is 1 over n squared. So we're going to take the limit. I'm not going to worry about the absolute value right now because both of these are positive for all terms, but typically you would have the absolute value here. You take and substitute in n plus 1 for the numerator, and the original is used for the denominator. And this can be simplified then algebraically to look like this, where we have n squared divided by the quantity n plus 1 squared, and that gives us 1, and so there's a big question mark there. Now, we know this one is convergent by the p-series test, and so in this case, we get a ratio test that gives us a value of 1. We don't know what that means. However, we could use a different test and determine convergence. Okay, then the second one is 1 over n. So we have the limit as n goes to infinity of 1 over n plus 1 divided by 1 over n. Again, that can be simplified to give us n over n plus 1. That's, of course, 1 again, big question mark. However, for the same reason, we know that this one is divergent by the p-series test. Okay, so all this to say that if the ratio test gives you a value of 1, it's inconclusive. So we do not know if it's convergent or divergent. Here's a very simple example that proves that that is meaningless, because in one case we got 1 and it was convergent, and in one case we got 1 and it was divergent. All right, let's take a look at example 13. Now typically with the ratio test, you're going to have situations where you have possibly n in the power, possibly n in the base, maybe you have a factorial, everything is kind of jumbled up together. Many of the other series that we've discussed or we've studied so far have been sort of in a simpler form, where maybe the n is just in the base, or maybe n is just in the power. But often when you have a combination of where n is, that's going to many times be the ratio test. So in this case, we have n to the third, so we have n in the base, and we have 3 to the power of n, so we have n in the power. So there's a combination of items. In addition, we have an alternator. So because of all of these elements, the ratio test is sort of our go-to when it comes to something that's a little more complex like this. So our first step is that we take the limit as n goes to infinity. We are going to apply the absolute value, and we're going to do n plus 1 for all the n's that we see in the original. So we have, actually I'll just make this all over 3 to the n plus 1. And what I'm going to do is I'm going to show you sort of the long way to do this, and then we will simplify the process as we get into this a little bit. So that's your numerator. Your denominator is negative 1 to the n times n cubed divided by 3 to the n. You do want to have a little bit of a simpler strategy with this because the ratio test can take a long time otherwise. So I'm going to get rid of the alternator here because we're taking the absolute value. And so the alternator is going to be gone. No matter if it's -1 to the n plus 1 or it's -1 to the n, the alternator is gone. So then what we get is n plus 1, that quantity cubed, divided by the 3 to the power of n plus 1. I'm going to make that 3 to the n times 3 to the first. So I'm going to split that up. There's a reason for that. And then we're going to multiply by the reciprocal of the denominator, which is 3 to the n divided by n cubed. Remember, we eliminated the alternator simply because of the absolute value. Okay, we're able to cancel some stuff, which is why I did 3 to the n times 3 to the n plus 1. We're canceling those. As we take the limit as n goes to infinity, n plus 1 cubed divided by n cubed will cancel to 1. Remember, because we're taking the limit as n goes to infinity. So we're able to simplify that to a limiting value of 1. What this means is that we have a limit of 1/3. And 1/3 is less than 1. And since 1/3 is less than 1 by the ratio test, this particular series from 1 to infinity of our alternator times n cubed over 3 to the n is convergent. So that's an example of the ratio test. Let's try another one. We're going to do this problem in 2 different ways. So the first way we're going to do it is we're going to do the ratio test. It's going to be a little ugly, I'll warn you. So we have the limit as n goes to infinity. I'm not going to bother with the absolute value because, again, all of these terms are positive. What I am going to do, however, this time, is that I'm going to take and put in n plus 1 for all of the n's. However, I'm going to go ahead and immediately change to the multiplication. So notice in the previous problem, I set up the original as a sub n plus 1 divided by a sub n, and then I jumped into the multiplication. I'm going to do that right away. So normally, we would take the a sub n plus 1 term divided by a sub n. I'm going to take the a sub n plus 1 term and multiply by the reciprocal of a sub n. So in other words, I'm going to multiply by n factorial over n to the n. Okay, so again, I'm just simplifying the algebraic process there just to save a little bit of space. Okay, the next step is that I'm going to simplify this down a little bit. Now, as a side note, if I have, for example, n plus 1 factorial, that means that I have n plus 1 times n minus 1 times n minus 2, and so on, okay? I'm going to write n plus 1 factorial as n plus 1 times n factorial. Okay, so the reason that we're going to write it that way is to simplify this limit. So the limit is going to be, and I'm going to sort of do a similar thing in the numerator here. I'm going to take n plus 1 to the n times n plus 1 to the first. So I'm going to split up that. But I'm going to rewrite the denominator as n plus 1 times n factorial so that ultimately I can cancel my n factorials. So notice we can cancel n factorial here. We can also cancel n plus 1. And we're left with the limit as n goes to infinity of n plus 1 to the power of n divided by n to the power of n. And I'm just going to start to rewrite this a little bit. This is a limit that we saw way back in chapter 2. It's a very famous limit. It's a very famous number. So I have all of that to the n. So n plus 1 divided by n to the n. That can be rewritten as 1 plus 1 over n to the n. And if any of you have noticed it already, again, this is one that's very famous. However, we don't use it a whole lot, but we did talk about it in chapter 2. This is the limit definition of e. So this is equal to e. You could actually figure this out by using logarithmic change and looking at the limit as our logarithm and pulling down that exponent. That's what we did in chapter 2. It's a really long problem, and what we got out of the deal was e. So e is greater than 1, which means that the original n equal to 1 to infinity of n to the power of n over n factorial is divergent by the ratio test. Okay, so that's one strategy. That's one way to do this. There is, however, another way to do this. And again, keep in mind that you have 10 convergence tests, and let's say that a problem allows you to apply 3 different tests to the problem. They all should have the same conclusion. It's not like one test would give you a divergent series and the other test would give you a convergent one. They should all agree. So what I'm going to do with this one is I'm going to list out some terms of the original. So I'm going to say that n, I'll change colors here. So n to the power of n over n factorial is basically n times n times n times n for a very long time times n. And n factorial, I'm just going to kind of switch around the factorial. I'm going to make it 1 times 2 times 3 times 4, and I'm going to do that for a very long time until I get to n. So if I think of this fraction, and I know it's infinite, but if I think of this fraction and I compare it to simply n divided by n, this fraction is larger than that. So n divided by n, which I know is 1, is smaller than the series that I'm dealing with. Now the series n divided by n, which I know is 1, is divergent. And if it's 1, that would just be simply by the nth term test, or just intuition, basically. And so therefore, this particular series from 1 to infinity of n to the n over n factorial is divergent by the comparison test. And that's faster probably than the ratio test. But either way, you can do this 2 different ways, which there are a handful of series that you can certainly do 2 different ways. Okay, let's go ahead and move on to the next problem. All right, we're on example 15, and ask for which of the following series converge. Now keep in mind, we're studying the ratio test right now. However, you can use any series that makes any kind of sense. The p-value here is 1/2, which is less than 1. So this particular one is divergent by the p-series test. That was a really fast one. So that's gone. Okay. What about the second one? Well, it has a power of n and a factorial. That's probably going to be the ratio test. So let's take a look at using the ratio test here. So we have the limit of the absolute value. I don't really care about that because all the terms are positive. So we have, now I'm gonna shorthand this a little bit. So remember, 3 to the n is the same thing as 3 to the n times 3 to the first. And n factorial is the same thing as n plus 1 times n factorial. Remember, this is going to save you time. Times the reciprocal, which is n factorial divided by 3 to the n. So again, remember that we're ultimately taking, I'll write this over here just to make sure it makes some sense. We're taking the limit as n goes to infinity of 3 to the n plus 1 divided by n factorial divided by 3 to the n, go back here. So it's 3 to the n plus 1 divided by n plus 1 factorial, please change that, divided by 3 to the n divided by n factorial. Okay, if you take that and simplify it, you get what I have here, just simplified down a little bit more quickly. And it's important with the ratio test that you get to the point where you can do that. Otherwise, like for instance, this multiple choice problem, you're going to spend way too much time working from the very beginning. So try to get algebraically down to where we are here with the ratio test. Okay, I'm going to erase this really quickly. Okay, let's continue. So we're going to cancel some stuff here. We're going to cancel 3 to the n. Keep in mind that when you look at the n factorial, that cancels. But let's just rewrite this really quickly so we see what's happening. So we have n going to infinity, and our leftover is 3 divided by n plus 1. And the limit as n goes to infinity of that is 0, which is less than 1. So this is convergent by the ratio test. All right, last but not least, we have e divided by pi to the n. That is our r value. And the absolute value of e divided by pi is less than 1. So this is convergent by the geometric series test. So we have option 2 and option 3, which is letter E. Okay, let's do one last one in this video. So we're going to have example 16, and I'll try to change colors here. So the first one, you have n as a power, you have n as a factorial. I think we're looking at using the ratio test for that one. So we have the limit as n goes to infinity, all positive terms, so I don't really care about the absolute value right now. The 8 to the n is going to be 8 to the n times 8 to the first divided by n plus 1 times n factorial times n to the n factorial, and then 8 to the n. And we're going to simplify this down. Let's cancel some stuff. So 8 to the n is gone, n factorial is gone. So we're left with the limit as n goes to infinity of 8 divided by n plus 1. That's 0, which is less than 1. So that's convergent by the ratio test. Okay, that's a good one. We want that one. And then we're going to look at the next one and kind of go through the same exact logic with that one. You have a factorial, you have a base. So I'm thinking we're going to do the same thing for number 2 here. Oops. So we have the limit as n goes to infinity. Same thing, they have all positive terms. We have n plus 1 times n factorial divided by n plus 1 to the 100th power times n to the 100th power divided by n factorial. Okay, with this one, we're going to cancel a few items here. Let's see. So the n factorial cancels. Now, this one's a little bit kind of more interesting because when you take the limit as n goes to infinity, n to the 100 divided by n plus 1 to the 100 is really going to cancel to 1 because I know n plus 1 to the 100 has more items there, but the bottom line is that, and maybe I won't even show that cancellation right now, the idea with the numerator is that you're going to have, I'll try to write this out as a communication tool. So you have, you know, if you were to distribute it all out, you would have n to the 101 plus a little bit there divided by n to the 100 power plus a little bit there. And we don't really care about the extra items because the degree is smaller than, for instance, 101 in the numerator and 100 in the denominator. And so this particular limit is going to go to infinity. And the ratio test says that if that's true, then you have a divergent series by the ratio test. Okay, so that one's going to be out. We don't want number 2. And then let's take a look at number 3. Now with number 3, you have n as a base in all values there. I'm looking at it in terms of the ratio test, thinking that it's going to be a lot of substitution. I'm thinking about the limit of it is 0. That doesn't help me. It's definitely not geometric. It's not a collapsing sum that I want to tackle right now. I cannot integrate it, so I don't want the integral test. It's not a p-series. Comparison would be challenging because of all the different n's that are in there. And so what I'm looking for actually with this third one is the limit comparison test. One of the things that alerts me to the limit comparison test is that this is a rational function. It's a polynomial divided by a polynomial, and it's sort of a textbook limit comparison test. So what we're going to do is we're going to take the original n plus 1 divided by n times n plus 2 times n plus 3 And I'm going to divide this by 1 over n squared, simply because I want to make sure that the rational function has the same degree in the top and the bottom. And this would give me the limit as n goes to infinity of, I'm just going to write it as n plus 1 times n squared divided by n times n plus 2 times n plus 3. We could distribute this, but I don't really care too much. Top has a degree of 3. The bottom has a degree of 3. The ratio of the leading coefficients gives me 1, and that's greater than 0. So since the series 1 over n squared converges by the p-series test, then the series that we're trying to analyze here also converges by the limit comparison test. So we're looking at having option, let's see, 1 and 3, which is going to be letter D. Okay, that's it for this video. We will have one more video on section 8.4, which will cover the remaining examples. And in those examples, there is some new information, so that video will be worth watching. Thank you.